Welcome in everyone. In this video, I am going to go over related rates. So first I want to go over why is related rates. Then I'm going to go over the pieces and parts needed for solving a related rates exercise. And then we'll get into some examples, and yes, there will be trig in some of these examples. Let's get into it. Why is related rates? Well, related rates are helpful to understand the relationship of how variables change with respect to time. And time ends up being this invisible variable that we will use in all of our scenarios. So as you can see, we're trying to understand the relationship of how variables change. And these words here, how variables change, we're talking about a rate at which the variables are changing, otherwise known as a rate of change, and how those rates are in a relationship with each other, or how they are related to one another. So that's why we're taking a look at related rates. In this slide, I'm going to go over how you can take a derivative with respect to a variable that isn't even in the equation. If you don't recognize this particular equation, this gives you the volume of a cone. And the volume of a cone, it depends on the size of the radius and the height of that cone. All right, so how do you take the derivative with respect to t here? Because, I think the stereotypical example is pretend you have one of those conical cups from a water cooler, and the volume of the water can change with respect to time. So how is the radius of the circle changing at a particular time? How fast is the height of the water in the cup changing at a particular time? These are all questions we could ask about this, but in order to take the derivative, what we're going to do is we're going to take the derivative of both sides of this equation with respect to t. And what this does is it creates an implicit differentiation problem. And we will also inherently be using the chain rule here. So we can take the derivative of a variable like normal. So this is v to the first power, bring down the 1, and then we would subtract 1 from the exponent, so it would be v to the 0. But then we have to take the derivative of v with respect to time. So we'll end up with a 1 dv dt. From there, if you look at the left side of the equation, we will end up having a product rule. So the pi over 3 will just come along for the ride. I'll kick that out front. That will be pi over 3 times the product rule of something here. So what that will be then is we can say the first times the derivative of the second with respect to t, and the derivative of h will take place just very similarly to what we did with v over here. So we will end up with r squared dh dt. Technically 1 times dh dt, but again, we don't need the 1. Then we will take the second times the derivative of the first. So the second here is h, and the derivative of the first this time is 2r, but then because we're taking the derivative with respect to t, those variables don't match, we have to multiply by dr dt. So 2r dr dt, and we can just add these together. So this is where all of the little pieces parts come into play. What do we have in front of us? In the original equation, we have a v, so maybe we know the volume, or maybe we can figure it out. But then we also have this dv dt, which is basically saying, how does volume change as time progresses? And you can see for each variable, we have this same pairing of the actual value and the rate at which that value is changing. So we have the radius in our derivative, as well as the rate at which the radius is changing. We have the height in our derivative, and we have the rate at which the height is changing. So basically, we are looking for an actual variable and the rate that the variable is changing. So these are important things that will be given to you, or you'll have to figure out as you work through examples. Speaking of examples, let's take a look at this one. A point is moving along the graph of y equals 1 over 1 plus x squared at a rate of dx dt equals 6 inches per second. We want to find dy dt when x is at 2. And some things before I start going really far into this. The rate here given is just a horizontal rate. So the horizontal rate that this point is moving along the graph is at 6 inches per second. And we also have an accompanying piece of information here with this. We have the horizontal rate, which relates to x, and we know the value of x that we're looking for. It's 2. So how are you going to figure this out? Well, the first thing I like to do is write down the equation. So we're going to be taking the derivative of this equation with respect to t. From there, what we're going to do is I'm going to write down everything I know. So 2 variables. And I know I have the variables x and y. Now, what do we know about the variables? We don't know the y value, but we do know the x value because it's given to you right here. X is 2. So let's write that down. Is there a way we can figure out what the y value is? Sure. We can just substitute the 2 into this original equation here for x and figure out y. And will it be important? I don't have any idea. I think it's good to have the information going into it, so I'm going to say this will equal 1 over 5 because that's what you get when you substitute 2 in for x. The next bit of information here is going to be dx dt because x will change with some rate, and dy dt. All right, so do we know any of these rates? Well, yeah, we know dx dt, it was given to us. The rate at which x is changing is 6, and it's positive. And we're actually being asked to find dy dt, so I'm just going to leave that as a question mark. I don't know what that is. So the variables and their rates are done. So again, equation, variables and rates. The third thing I'm going to do here is actually take the derivative. So 3 derivative. And taking the derivative of this will give you dy dt equals negative 2x dx dt all over 1 plus x squared, the quantity squared. Now to get from here to here, the left side is pretty easy. You just have to take the derivative of y with respect to t, which will be 1 dy dt. The right side, however, uses the quotient rule, so the denominator times the derivative of the numerator, which is 0. That all cancels out, thankfully. Minus, that's where the minus comes in, the numerator times the derivative of the denominator. And the derivative of the denominator here is just 2x. That's where the 2x comes from. But since we're taking the derivative with respect to t, we will have the dx dt right afterward. All over the denominator squared. Cool. So we're trying to find dy dt. which means we can just substitute these values in as necessary and simplify to find dy dt. Like this. So I substituted the 2 in for the x, I substituted the 6 in for dx dt, and I substituted 2 in for the x in the denominator as well. Now you might have noticed that we did not use the y value here, but we had it at our disposal in case we needed it. All right, last thing we need to do then is simplify this numerator. Negative 2 times 2 times 6 is negative 24. And lastly, we have 1 plus 2 squared, that's 5. The whole thing squared is 25. And those are the numbers, negative 24 over 25. But we do have units hiding up here, inches per second. And we need to include those units in our answer. So when x is moving along this graph at 6 inches per second, when it hits the point in the graph where the x value is 2, the y values are decreasing due to the negative here at 24 over 25 inches per second. A spherical balloon is being inflated at a rate of 800 cubic centimeters per minute. How fast is the radius increasing when the radius is 30 centimeters? All right, this one's going to be a little more involved as we don't have an equation to start with. So you can take a few seconds to Google the volume of a sphere, or you can just wait, and here it is. So we have the volume of a sphere equals 4/3 pi r cubed. Not bad. We're still sticking with only one variable on the left and one variable on the right. Okay, so we know the volume is being inflated, it's being increased at a rate of 800 cubic centimeters per minute. So that's part 2, right? Let's figure out what we know. This will be volume and radius. So do we know the radius? We in fact do know the radius. It's 30 centimeters. Do we know the volume? We don't know the volume, so we'll leave that alone for now. But we do know the rate at which the volume is changing with respect to time. Is 800, and it's asking us to find the rate at which the radius is increasing. So we don't know that either. I'm going to go ahead and just compute the volume very quickly by substituting 30 in for this r, which ends up being a whopping 36,000 pi, let's see, volume cubic centimeters. Yeah, that's a big ol' balloon. Anyway, so we found everything we need to know. Will we use this? Who knows, but we have access to it if we need it. So we have everything we need to know about V. We have everything we need to know about R, including the fact that we're searching for the rate at which the radius is changing. And now we're going to take the derivative of this equation. Let's say derive. There we go. So taking the derivative with respect to t of both sides will give you dv dt on the left and 4/3 pi is all a constant being multiplied to the variable r there. So we'll have 3r squared dr dt. Okay, not too bad. We can do a little cleanup on the left side here. I can reduce a 3 with a 3, and this will make the equation dv dt equals 4 pi r squared dr dt. All right, Once we have that, we just have to substitute numbers in and solve what we're solving for. So I see we can substitute a dv dt in. Yep, we have 800 that'll go here. And it looks like the only other thing we have available to us is r. So r, we'll substitute a 30 in there. And we're searching for dr dt. Oh, we didn't need v here, but that's okay. We have it in case we need it. Let me substitute those numbers in. There we go. Now I can clean up this right side again. 30 squared is 900, times 4 is 3,600, so we'll have 800 equals 3,600 pi dr dt. And then if I want to solve for dr dt, all I have to do is divide by 3,600. This is also only 800. There we go. So divide 800 by 3,600 pi equals dr dt. Now, of course, this fraction can be simplified to 2 over 9 pi, and then the units, of course, here are in centimeters and in seconds. So here's how fast the radius is increasing. All right. I guess a couple other things I want to say here is that we were searching for how fast a radius is increasing. And when you look at the radius units, it is just in centimeters, right? Since we have to cube a radius to find the volume, the units here will be in cubic centimeters for a volume. The other part of this is we are searching for a rate. So the units of time need to match up. We saw up here, as you can see, do as I say, not as I do. This is minutes. There we go. So the time unit up here is minutes. So the time unit down here should match that. This example is pretty prototypical for a Calc 1 course in a related rates section. A ladder leaning against a vertical wall has its base pulled away from the wall at 2 feet per second. If the base is 7 feet away from the wall, how fast is the top sliding down the wall? Now, when I say vertical wall and all this stuff, really what's happening here is that the wall is vertical and the ground is completely horizontal. And it's important to make that distinction because there will be a 90-degree angle here. So I'm going to go ahead and draw a picture because a picture is going to make the most sense of what the heck is going on here. All right. So we've got a 25-foot ladder, and the base of that ladder down here is 7 feet from the wall. And what's happening is this base is being pulled away from the wall at 2 feet per second. And that's everything we know from the scenario up here. But we don't have yet written down what are we trying to find. What we're trying to find is how fast the top is sliding down the wall. Okay, so again, I mentioned, I didn't notate it, we have a right triangle here, and you can see that we're trying to relate something about the long leg to something about the short leg, right? We know everything about this short leg. And we're trying to figure things out about the long leg, and even we know the hypotenuse. So this is going to use the Pythagorean theorem. I will notate this slightly differently than what you might have seen it before, but the horizontal distance I'm going to call x, the vertical distance I'm going to go ahead and call y, and then the hypotenuse I'll just call h. So this means we will have an equation that looks like this. X squared plus y squared equals h squared. All right, so there it is. We've got our equation. Second thing I want to do is write down all the information I know about all of these variables and their rates. So 2, I know I have 3 variables, x, y, and h. And I know x is equal to 7 feet. Y we can figure out using the Pythagorean theorem because we know that the h, the hypotenuse, is 25 feet. Now, you can go through and do this and figure it out for yourself, but I can tell you the y value here is 24 feet. Next, we need to know write down what we know about the rates. So I know the rate at which x is changing is 2 feet per second. And I'm going to point out that this is a positive value, because what's happening with this x distance is that right now, right at this very moment, the distance between the base of the ladder and the wall is 7 feet. But that distance is going to be getting bigger. So it has a positive rate of change. The dy dt is exactly what we're trying to figure out. And dh dt we know, even though it might not be given, in this scenario, this is the length of the ladder. The length of the ladder is not changing. The length of the ladder stays 25 feet the whole time it's being pulled away from the wall. So that means the rate at which the length of the ladder is changing is 0. Now that we know this, we can go ahead and move to the derivative of this equation. And so essentially, again, we just get to take the derivative as normal. And then since we're taking the derivative with respect to t, we have to apply the chain rule to all 3 of these variables. So dx dt, dy dt, dh dt, and now you have the derivative of this equation. Now we can do a little bit of simplifying before we even get into substituting values in for our variables and rates, and that is by dividing every term by 2. So here's the cleaned up equation of that. From here, we can just start substituting every number we know into the equation. So 7 for x, 2 for dx dt, 24 for y, we don't know dy dt, 25 for h, and 0 for dh dt. And I'm just going to go ahead and stop there. 25 times 0 is just 0. So the entire right side of this equation just becomes 0. Like this, and I'm running out of space, but if you multiply this out to get 14, subtract it from both sides, and then divide by 24, and of course simplify negative 14 over 24, you'll get negative 7 over 12 feet per second. And this is the first example in this video of a negative rate. Does this even make sense? Well, going back to what I said about this distance increasing, so this rate is positive. This distance, as the ladder slides down the wall, is decreasing. That means this rate will be negative. As an extension to the ladder problem, we can look at some trigonometry of it. Since it is a right triangle, right after Pythagorean theorem, I start thinking of sines, cosines, tangents, etc. So here's the question: how fast is the angle between the ladder and the ground changing? And in this scenario, we are keeping everything the same from the last scenario. The base of the ladder is 7 feet from the wall. The length of the ladder is 25 feet. The point at which the top of the ladder reaches the wall is 24 feet from the ground. It's being pulled 2 feet per second away from the wall, and it's sliding down, as we figured out in the last part, negative 7 over 12 feet per second. So let's see, how are we going to figure this out? Well, since the angle is being placed here between the ladder and the ground, we'll end up using cosine because this is the adjacent side and the hypotenuse. So let's go ahead and write that out. So our equation will be cosine of theta equals x over h. And as we write down the equation, you want to keep in mind, we're going to use variables for everything. All right. Now, what are we going to substitute in for those variables? We will bring back all of the values we had from the last slide. Remember, this was x down here and y over here, and I called this h for hypotenuse. And what we're trying to figure out is d theta dt. Now in this part of the example, I don't know what theta is. We could figure it out, but also it's not going to matter because we're not actually concerned about the angle. We're more concerned about the cosine of this angle. So I could, if I wanted to, figure out the cosine just by simply dividing adjacent over hypotenuse. As you can see here, right? Adjacent over hypotenuse. All right, next little bit here. Let's take the derivative. So when you take the derivative of this equation, you'll get negative sine of theta equals, we're going to have to use the quotient rule on this side. So h dx dt minus x dh dt all over h squared. Now let's say you're going through this example and you make this mistake I made here. You remembered that you're taking the derivative with respect to t on the right side of this equation, so you have a dx dt and a dh dt. Fine. But something is very missing here. We had the derivative of sine. We didn't take the derivative of theta. And one easy way to understand that there needs to be a d theta dt here is that's what you're solving for. You can't solve for it if it's not in the equation. So d theta dt, don't forget it. All right. Now before we get too happy in substituting our numbers in place, I'm going to do it in kind of a specific order. I am going to remember that dh dt is 0, and that makes life a lot easier. When you substitute 0 in here, this whole term becomes 0, and subtracting 0 doesn't change the first term. So this whole term zeroes out, which means really we just have this fraction here. And you can see there's an h that will reduce from the numerator and denominator, and that will leave you with the following equation. All right, now we can go substitute everything in. So I'll put 2 in for dx dt, 25 in for h. We're trying to solve for d theta dt, but we have to figure out what this negative sine of theta is. So let me get this in here. 2 over 25 equals d theta dt. But very similarly to what I said, we don't need to know what the angle is. We can figure out what the sine of that angle is just by using the triangle we created over here. The sine of this angle is the opposite value divided by the hypotenuse. So 24 over 25, but it's got to be negative. Okie doke. Now we can just multiply both sides by negative 25 over 24. And would you look at that? These reduce really nicely. This whole side reduces here, leaving you with negative 1 over 2 radians per second. And again, we have this weird negative number here. And that makes sense because as you pull the base of the ladder further and further from the base of the wall, the angle here will get smaller and smaller and smaller and smaller until that angle is 0, because the ladder will also be flat with the ground. And just to point out, radians are the preferred unit of measurement when coming to angles. Last example. The morning of a day, the sun will pass overhead. The shadow of an 80-foot tall building is 60 feet long. And I'm going to say it here, on completely flat ground. At that moment, the angle the sun makes with the ground is increasing by 0.27 degrees per minute. How fast is the shadow decreasing? I really think a picture would be ideal here. All right, there's a good looking picture. I had no help with the straight line tool whatsoever. So what's happening here? This building is 80 feet tall, and yes, one tick mark up here means feet, and the shadow here that's being cast is 60 feet long. The other thing we know here is that this angle is changing. D theta dt, it is increasing at 0.27 degrees per minute. Now, I just got done saying that the preferred unit of measurement for angles is radians. So I'm going to go ahead and convert this to radians. And it will be this value right here, 3 pi over 2,000 radians per minute. Now, normally I go into finding the equation first and then finding the variables and everything we know about the variables and the rates associated with them. But I'm going to start with the variables here first because reasons I'll explain once I get that stuff written down. Okay, so here are all the variables and the rates associated with them. Where did I come up with these variables? Well, I noticed again we have a right triangle, we have a long leg, a short leg, and a hypotenuse, otherwise known as a horizontal leg, a vertical leg, and a hypotenuse, which is 100 feet from the Pythagorean theorem. And we don't know the angle here, and that's fine. We do know how fast the angle is changing, so that's fine. And dx dt is the goal. We're trying to figure out how fast is this shadow decreasing. So what do we know about dy dt or dh dt? Well, it turns out that as the sun passes in this direction over the building, the shadow will get shorter and shorter and shorter and shorter. We know that. They told us that. That's what we're trying to figure out, is how fast is the shadow shrinking. But as the sun progresses, say to here, the distance of the hypotenuse also changes. From here, this is a shorter distance. But what doesn't change is the height of the building. So when we come here for dy dt, we know that will be 0 because the height of the building does not change. But since the ray of sunlight here will change distances over time, we can say that it's going to be negative, but we have no idea what that rate is. So the next thing we want to do is figure out which equation we want to use. So we want to relate something with this angle with this edge, because when the derivative is 0, we know it's going to be working a lot easier. Things will simplify easier. And this edge, because we're trying to figure out how fast it's decreasing. So we will use an angle, its opposite side, and its adjacent side. So this tells me we will be using tangent in the next slide to solve for dx dt. So keeping the pertinent information from the previous slide, we know that tangent of theta will be y over x. And now we are ready for the derivative. So when you take the derivative of the left side, it'll be secant squared theta d theta dt will equal the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And this works out very nicely because, again, we know dy dt right here is 0. So what that will do is it will zero out this entire term, and we will just be left with this fraction here on the right side. So while I write that out, what I want to do is kind of tackle that secant squared on the left side at the same time. Now we don't know what this angle is, but we can figure out what the secant of that angle is, and that will be equal to the, what is it, the hypotenuse over the adjacent side. And that is because secant is the reciprocal of cosine. Cosine being adjacent over hypotenuse. If we reciprocate that, it'd be hypotenuse over adjacent. So that will come in the next step. So d theta dt. That was a cleanup step. Now we can write things out here. Here are all of the values substituted into the equation. Now all we have to do is substitute for dx dt by dividing both sides by -80 and multiplying both sides by 60 squared. If you apply the square to the 100 and the 60, we will have some 60 squareds that reduce nicely here. So let's get rid of those. In the numerator, we will end up with 20,000 pi, and in the denominator, we will end up with 240,000. And it's supposed to be negative. All right, then we can just simplify this with this and get -1 pi, or negative pi over 12, which is approximately 0.26 feet per minute. And that's going to be a negative value, which makes sense because the distance of the shadow will be getting shorter. I really hope this video helps you out.